We start Chapter 6 by reviewing basic facts about angles. We learn about a new system of measuring angles around a circle and develop formulas for arc length and area of a sector. Precalculus Online begins now. Angles and their measures. So here's where we begin the trigonometry portion of this course. So we'll review basic angle facts, standard position is a big deal, and then we'll talk about the radian, arc length, and area of a sector. So let's start with angles. And you know what we have here. We have angles. So we have the vertex of the angle is this point, and then we have two rays or two sides. And we'll have the initial side or initial ray, that's the first one. And then we have the terminal ray or terminal side. And then the angle is formed by the opening. Now we use an arrow inside here to denote which way the angle is opening. And oftentimes we use Greek letters to denote the angles themselves. This particular Greek letter is known as alpha. First letter of the Greek alphabet. And since this angle is opening up counterclockwise, we say that it is a positive angle. So counterclockwise, CCW, is equal to positive angle, because we had to make one of them positive, so they chose this one, and there's some good reasons behind that. So counterclockwise is positive angle. And then let's suppose that we have a different angle, but it looks much the same, but this time it goes around the other way. Let's call this one beta. Beta is the second letter of the Greek alphabet, and incidentally, by the way, this is where we get our word alphabet, alpha beta, for our system of letters. Anyway, this one goes clockwise, CW stands for clockwise, and that makes this a negative angle. So counterclockwise is a positive angle, and clockwise is a negative angle. Let's look at standard position. So standard position requires two things. The vertex of the angle must be at the origin, and the initial side of the angle must coincide with the positive x-axis. So when we draw a standard position angle, we draw the standard xy coordinate system, and then in order to draw the angle, here's the initial side on the positive x-axis. The terminal side, of course, can be anywhere, and then it opens up, and we denote which way it opens up with the arrow and give it a name. In this case, this is theta. This is one of our more popular Greek letters for angles. And then we can also describe what this angle is by which quadrant it is in. So remember, the quadrant system goes 1, 2, 3, and 4. And we would say theta is a quadrant 2 angle. Please remember that the quadrants are denoted by the Roman numerals 1, 2, 3, and 4. Now we also going to have this other type of angle here. So let me start with this one. And it's standard position angle. And this time, let's say that the terminal side is here. Well, this is not just any angle, this is a right angle. Let's call this one gamma. And since it's not really in quadrant 1 and it's not really in quadrant 2, we say that gamma is a quadrantal angle, meaning that the terminal side lies on one of the axes, x or y, positive or negative, it doesn't matter. All right. Let's look at degrees. So we know what one revolution is. So one revolution is there, and that's 360 degrees. And so if I sort of flip that around, 1 degree has to be 1/360th of a revolution. We also have classification of angles. If an angle alpha is between 0 degrees and 90 degrees, we say that that angle is acute. If the angle is equal to 90 degrees exactly, that's a right angle. If the angle is between 90 and 180, we say that that angle is obtuse. And if the angle is equal to exactly 180 degrees, we call that a straight angle. Example 1, draw 45 degrees in standard position. So let's draw the grid here. And for standard position, we have the standard position angle starting with the initial side on the positive x-axis, and the 45-degree angle splits the first quadrant in half. It opens up like this, and that's 45 degrees. Example number 2, draw negative 120 degrees in standard position. So let's have the grid. And again, standard position angle starts with the initial side on the positive x-axis. 120 degrees is going to open up past 90 degrees and then another 30 degrees. So it's going to be about right there. We'll get to more of these angles specifically when we do the unit circle in the next lesson. But for now, this is good. Notice that it does open up clockwise because it is a negative angle. Let's look at the subdivisions of degrees, and much like time, where degree is an hour, the degree is split up into minutes and seconds, and it's actually the same divisions as well. 1 degree is equal to 60 minutes, and the symbol for minutes is this little prime mark, like an apostrophe, and then 1 minute is equal to 60 seconds. And the symbol for seconds is the 2 apostrophes there. Example 3, convert 32 degrees, 12 minutes, 45 seconds to decimal degrees. In other words, we just want to represent it in degrees and use decimals as much as possible. So, well, we know it's going to be 32 degrees. Then we have 12 minutes. So I need to convert 12 minutes into degrees. And the question is, how many degrees for how many minutes? Well, 1 degree is equal to 60 minutes. So multiplying by 1 over 60 is the conversion factor to go from minutes to degrees. Now, I don't really think about conversion factors as it has to be this one to do this unit to that unit. I put in the units first and then decide where the numbers go. So in this case, I had minutes, so I put minutes on the denominator so that they will cancel, and then I put degrees up here at the top so that that would be the unit that's retained. And then I ask myself, how many degrees for how many minutes? 1 degree is equal to 60 minutes, and I put those numbers in the corresponding parts. Similarly, plus 45 seconds, well, now I need to convert this. And so I'm going to cancel seconds, so that goes in the denominator. I am going to convert it to minutes first, and we know it's 1 minute for 60 seconds. And then I'm going to take that conversion, that is now minutes, I'm going to convert minutes to degrees, so minutes goes on the bottom, degrees goes on the top. It's 1 degree for 60 minutes. And if you want to skip this part where you split it up, then you can just realize that 3,600 seconds is equal to 1 degree. Well, you type this into the calculator, work it out, and you get 32.2125 degrees. Let's look at example 4. Convert 88.88 degrees to DMS, degree minute seconds. So the way I think about this is 88.88 degrees is equal to 88 degrees. We know that part. But then there are some minutes and there are some seconds. And it's our job to now figure out how many minutes and how many seconds. So I've already taken care of the first 88, the integer part. I now need to look at the rest of the subdivision of the degree. Well, what's left after the 88? 0.88. So I'm going to take 0.88 degrees, and I'm going to convert this to minutes, and let's just see what happens. So I want minutes. I need to get rid of degrees. So the degrees goes on the bottom, minutes goes on top. And we know it's 60 minutes for 1 degree. Multiplying this out in the calculator, I get 52.8 minutes. So the minutes portion here is 52, and that goes in the blank right there. Now I still have a subdivision of 0.8 minutes. That needs to be converted into seconds. And we know that 60 seconds are in a minute, and this works out to be 48 seconds. So the 48 seconds goes in the seconds position. So the answer is 88 degrees, 52 minutes, 48 seconds. All right, here you have an exploration. Go ahead and follow the link that was given to you on the website and go to student.desmos.com and find this activity. Run through the activity to determine what exactly a radian is. Go ahead and pause the video at this time, complete the activity, and then come back to the video. All right, so hopefully you had a chance to do the activity. So let's figure this out. What exactly is 1 radian? Well, 1 radian is the angle formed when the central angle of a circle of radius r subtends, and the word subtends just means cuts off, subtends an arc of length r. So in other words, let's have a circle here on the grid, and we want to find the angle, and I'll just put it in standard position, no problem there, where when we have a radius of length r, then the angle is going to be called 1 radian when the arc length is equal to r. Now notice that it's the arc length going around the circle. It is not the straight line distance here from point to point. It's not that straight line green distance that you see there. It is the arc going around. So think of it as a piece of yarn or a piece of string that's being wrapped around the circle. When the string length, if you pull it taut and stretch it out to its whatever its length is, straight line, non-circular, when that length is r, then you should be able to draw the radius of the circle with the same length. And that's what 1 radian is defined to be. And this will become very, very important as we move on through pre-calc. Let's look at example 5. The circle shown has radius 4. Find the arc length AB. Well, the arc length AB is right here. And the radius is 4. That's 4 and that's 4. And the angle is 1 radian. Well, we know that 1 radian is the exact angle that subtends an arc whose arc length is also 4. So the arc length AB is also equal to 4. And that's question A. Question B. Given that AOB is congruent to BOC right here, what is the arc length AC? So what is the arc length going from A all the way over to C? Well, first let's recognize that angle BOC is also 1 radian because it's congruent to the other angle, and therefore the arc BC must be 4 as well because it's equal to the radius. So the total must be 4 plus 4 is 8. And then what we need to understand about this is the proportionality. When you had 1 radian, you had an arc length of 4. When you had 2 radians, you had an arc length of 8. So by doubling the angle, you doubled the arc length. And that is true for any kind of proportion. Let's formalize that on the next page. Arc length. Since arc length is proportional to the angle, S is equal to R times theta, where S is the arc length, R is the radius, and theta is the angle in radians. The in radians part is the most important part of this equation. If the angle is not given to you in radians, you cannot use this formula straight up. You have to do conversions, which we will talk about later. So let's look at the circle. And let's suppose that we have a standard position angle. It doesn't even have to be standard position really, but it's okay. And we look at the angle theta, and suppose that's in radians. We have a radius of R, then the arc length going around is S. And so that's the picture that goes along with this formula. S is equal to R theta. Let's look at example 6. Find the arc length subtended by the central angle of 0.5 radians in a circle of radius 6 centimeters. So we have the formula. S is equal to R theta. The radius is 6 centimeters. The angle is 0.5 radians. So we abbreviate that with rad. When we multiply this together, 6 times 0.5 is 3. And then the question is, what should be the appropriate unit? Well, remember what we're finding is an arc length, which is the length of the portion around the circle. So it should be a linear unit, and it is in fact centimeters. So we have centimeters here, and we multiplied it by radians. So what happens? Well, many times when you use radians in computations like this, the radian unit sort of vanishes. And the radian here is really just designed to tell us that we're in the right system of units, that the number corresponds to this proportionality ratio that we really need in order to get the numbers to come out correctly, especially with the S equals R theta formula. So what you have to do is you have to look and see if the radian is sort of a necessary measurement to keep as the unit or not. Since we're finding arc length, we know that arc length has to be some linear unit, centimeters, feet, miles, whatever, and so the radian goes away. Next, how many radians are there in one revolution? Well, let's develop that formula and that answer by starting with the arc length formula. S is equal to r theta. And let's just go ahead and suppose that we have a circle whose radius is 1. Well, what do we know about that? Then, for one revolution, the arc length is the circumference. Of the whole circle. So yeah, if we're going around the entire circle, then that arc length is actually the circumference of the circle. But arc length now equal to circumference is equal to 2 pi r. That's the formula for circumference. 2 pi r. But we know that r, because we're on a circle of radius 1, is equal to 1. So this is actually equal to 2 pi. So in other words, we had s, which is 2 pi, is equal to the formula r theta from the arc length formula. But 2 pi must be equal to 1 times theta, because the radius is 1, and that tells me exactly what the angle is in one revolution in terms of radians. It's 2 pi, solving this last equation for theta. So that gives us the conversion factor. One revolution is equal to 2 pi radians. And we'll use that over and over. Now, we want to use this to develop the conversion between radians and degrees. So how many degrees are in one revolution? Well, one revolution is equal to 360 degrees. But since it is one revolution, that must be equal to 2 pi radians. And there is the conversion factor for degrees to radians, perfectly acceptable one. We don't use this version too often because you can see that both numbers are multiples of 2. So if I divide both sides by 2, this is the one that we actually use. 180 degrees is equal to pi radians. But I think it's important to keep this in mind as far as the whole circle is concerned. 360 degrees is 2 pi radians. When we go to use conversion factors, we usually use 180 is equal to pi. 180 degrees is equal to pi radians. Let's look at some more examples. Example 8, convert 45 degrees to radians. So 45 degrees is equal to rad over degrees. There are pi radians in 180 degrees. Now if we're doing numbers that are sort of common numbers like 45, 60, 90, things like this, you want to keep your answer with the pi. The pi is an essential part of having a radian measure. So we'll just cancel what we can with the 45. And we know that 45 divided by 180, it simplifies to 1 over 4. So we get pi over 4 radians. Example 9, convert pi over 6 radians to degrees. Same thing here. So pi over 6 radians. The radians unit here is in the numerator, so let's put it in the denominator. And so let's convert 2 degrees, and we get 180 degrees divided by pi radians is equal to 1. So the pi's will cancel, and then 180 divided by 6. 180 divided by 6 is 30. So we get 30 degrees. Example 10, Convert 3 radians to degrees. Use a calculator and round to 2 decimal places. So 3 radians, multiplied by 180 degrees divided by pi radians. If you use your calculator, you get 171.89 degrees. Let's take a look at area of a sector. So suppose I have a circle, and we have a sector here like so, and I want to know what the area of this sector is. Well, I need a couple of things known about this sector. Number one, what is this angle right here? Call that theta. And number two, what is its radius? Now if I develop the formula knowing what I already have, the area of a sector is equal to the radian measure of the angle of the sector divided by 2 pi. And what that is giving me is the portion of the whole circle. And then if I have that portion of the whole circle, then I just multiply it by the area of the whole circle, which is pi r squared. We've taken this formula, and this is the idea behind the formula. You take the portion of the whole circle and you multiply it by the area of the whole thing, and you get the area of the sector. But we've taken this formula and we've simplified it. So notice that the pi's cancel, and the 2 is usually written in the front here as 1/2. So it's 1/2 r squared theta. What makes this formula so interesting is that as long as theta is in radians, this is the formula for the area of a sector of a circle, and nowhere inside of it does it mention anything about pi, because the pi part has sort of been incorporated into the radian measure. And so it's just 1/2 r squared theta. Example 11. Find the area of the sector of the circle with radius 6 formed by an angle of 60 degrees. So we want to use this formula. Area is equal to 1/2 r squared theta. Radius of 6 is no problem. Angle of 60 degrees is a slight problem, because what we need is the angle theta to be in radians. So let me go ahead and convert this to radians. So we'll divide by 180 degrees and multiply by pi radians. And that's going to be pi over 3 radians. So here's where the pi comes back into our formula. So we're going to have 1/2 times 6 squared times theta, but in radian form, so it's pi over 3. And 1/2 3 in the bottom, 6 squared is 36, and then pi, and then 36 divided by 6 is 6. So this is 6 pi, and that's the answer.